Hey everybody, we're back and here we go. We're starting chapter 3. Make sure that you download the note-taking guide for this section and use it. If you'd like to, you can always take them old-fashioned. So we're talking about exponential and logarithmic functions. I know that you've probably seen these before. We're going to go into some more in-depth with this. We're going to recognize and evaluate and graph exponential functions. So here is some important vocabulary. A transcendental function, you can read that in that first paragraph of the section, but some examples of non-algebraic functions or transcendental and functions that we're studying are exponential and logarithmic functions. And then the natural base E is called the natural number. So you've probably seen this before. And E is approximately, now it's an irrational number. It goes on forever. This is also called a transcendental number. And you'll see that it's closely related to both of these concepts of exponential and logarithmic. Anyway, the natural number E is approximately 2.718281, and it goes on forever. And again, we call this a transcendental number. And we call it that because it can't be written in finite terms. Okay, so let's talk about an exponential function. And you can read about this on page 180, but it's a polynomial function. Polynomial functions and rational functions are both examples of algebraic functions, which are the functions we've been studying, okay? An exponential function, which is new, we're going to be looking at it this chapter, it can be written as f of x equals some value for base a to the x, where our variable is in the exponent. Let me write this a little clearer. So we say a to the x, where a cannot be equal to 1, okay, because 1 to anything is just 1. But a has to be positive and not equal to 1. And x is any real number, including negative numbers. So let's just make sure that we know how to put this into a calculator. So this, you could use your graphing calculator, you could use your scientific calculator. If I was going to put in 5 to the 3/5 power, in your calculator, on your graphing calculator, you're going to hit the number 5, and then you're going to hit the button that looks like this caret. Okay, that just means exponent. And then you're going to go parentheses 3 divided by 5 end parentheses. And if I do that in my calculator, we go 3 caret parentheses 3 over 5. Or 3 divided by 5, I get exactly 1.93318204.5. And remember, a fractional exponent like this looks like 5 to the third, all the fifth root. So these are equivalent, but I want to make sure that you know that this is an exponential. It's a function with an exponent, basically. So let's talk about their graphs now, which are really the bigger overarching theme of our section. Okay, it says, so for a is greater than 1, aka it's positive, is the graph of f of x equals a to the x is increasing on, and actually, sorry, we're on this page right here. So again, this is positive, where a is positive. The graph of f of x equals a to the x, is it increasing or decreasing over its domain? So if I think about it, as x is getting bigger, what would happen to our overall function? So if I've got a bigger and bigger exponent, I'm going to get bigger and bigger as well. So it's going to be increasing. As x gets bigger, so does the overall value of f of x. So what about if a is positive, the graph of a to the negative x, is it increasing or decreasing? So remember, negative x is like saying 1 over a to the x. So remember, as x gets bigger, your denominator is getting bigger, which means if your denominator is getting bigger, your overall value is getting smaller. So we call that decreasing. As x gets bigger, our overall value for g of x or f of x is going to get smaller and smaller and smaller and approach 0. So for the graph of y equals a to the x, or y equals a to the negative x, where a is positive, the domain is all reals, okay, because we can put in any value for x, and in interval notation we say from negative infinity to positive infinity. And the range for both of them, if we look at these graphs, is from 0 to infinity. Now let me show you what these graphs look like. Okay, we don't have a lot of room here, but I want to show you what these graphs look like. I'm going to do it over here in this little part of your notes on top of right here. So if I'm looking at this, I'm going to give you 2 graphs, okay? So if I've got f of x equals a to the x, the graph of that, remember, when anything is 0, anything to the 0 power is 1. So a to the 0 would be 1. And as x gets bigger, it's going to be growing like this. And as x gets smaller, it's going to go closer and closer to 0. And then for f of x equals a to the negative x, again, I know if x is 0, it still gives me that value of 1 here. But instead of getting bigger, it's going to be getting smaller, okay? And as x gets smaller, the value is getting bigger. So do you see how this here is as x gets bigger, it's increasing? And on the right side, where a is to the negative x, as x gets bigger, we are decreasing in the value. So that's what those parent functions look like. These are pretty important, so make sure that you have them in your notes, that these are the parent graphs for those super important exponential functions. Okay, so let's keep going. And it says, and the intercept, meaning the y-intercept. Do you see how both of them have a y-intercept? They both have a y-intercept at y equals 1. And that's because anything to the 0 power is always 1. Okay, so just keep that in mind. They also have y equals 0 as the horizontal asymptote. That's because it never crosses that x-axis into a negative value. Okay, so looking at this one here, it says sketch the graph of the function 3 equals negative to the negative x. So if I were to make my own xy chart, I could say, okay, let's just find some values for x equals -1, 0, and 1. So 3 to the -1 would be like saying 3 to the 1, which is just 3. So at x equals -1, y is 3. And this is f of x equals 3 to the negative x here. And then 3 to the -0 is just 3 to the 0, which is 1. And then 3 to the 1, 3 to the -1, I should say, is 1 over 3. So at x equals 3, y equals 1/3. So our graph is going to look like this. Okay. So now let's talk about the natural base e. Remember, e is our natural number, and the natural exponential function is given by the function f of x equals e to the x. Our x is still in the exponent, but our base is now the natural number. And in order to put this in the calculator, I just want to make sure that you know how to put it in a calculator. You're actually going to use your second key, and right to the left of your calculator, it's the third one up from the bottom, you're going to use your LN key. You can write that a little bit better. LN, which the second LN, you should see on your screen that it says E. Okay, so second LN equals E. So you're going to go second LN, and then you're going to hit your caret key, which means raises to the power of parentheses 3 divided by 5. And in your calculator, you should get, let me pull that up. So you go second ln, third from the bottom on the left, which is e, and you should see e to the, actually you don't have to hit your caret key. It should already show up for you on your calculator after you hit second ln, and then we're gonna go parentheses 3 divided by 5. And we get equals 1.82211188. Okay? So now for the graph of f of x equals e to the x. So remember, this is an exponential graph. The only difference is the base is the natural number instead of some other random number for a. So again, the domain is still going to be all reals, or we say from negative infinity to infinity. The range is still from 0 to infinity because it doesn't cross the x-axis, and the y-intercept is still y equals 1, so it still has all the same properties as our exponential functions before. And then there's this little kind of fun math note that the number e can be expressed by the expression 1 plus 1 over x to the x power for large values of x. So if you use that function, it gets close to defining what the number e looks like for the biggest values of x. And then the last one is we're going to be talking about an application, okay? And actually, I think we're missing, that's okay. You got it on your page. I'm missing it on mine, but I'll write it in. That's okay. So we have this formula to calculate exponential types of investments. So we've got something called compounded interest, okay? And compounded interest looks like this, that the amount equals the principal invested times 1 plus r, which is the interest rate, over n, which is the number of times compounded per year, to the n, which is again the number of times compounded per year, to the t. So again, a equals the amount, p equals the principal, meaning the initial amount that you give or that you invest, r equals the percentage rate in decimal, n equals the number of times that it's compounded per year. And so like it depends on how many times. So if it's monthly, it'd be 12. If it's weekly, it'd be 52. If it was semi-annually, it'd be 2. Okay? And then t equals the amount of years, or time in years, okay? And then for continuous compounding, that's a different formula. We say a equals e. This is a continuous number, which means we're going to use that transcendental number e. Sorry, I forgot to put the p. P times e to the RT, where again, p is still principal, r is still the rate, and t is years, okay? So let's just say, for example, this is in your example number 4, if the amount in your account after 10 years and $6,000 is invested at an interest rate of 7%. We're going to find A, the amount if it's compounded monthly. So first thing I notice, if it's compounded, we're going to be using this blue compounded function right here. A equals P times 1 plus R over N to the NT. And it tells me this is 6,000 is how much we invested. That's P. Our interest rate is 7%, so that's R equals 0.07 because that's in decimals. And then T is our time in years. And then for part A, this is compounded monthly. There's 12 months in a year. So from here, we know that N equals 12. So let's go ahead and calculate that. A is the amount that we're looking for. P is $6,000 that was invested times 1 plus R, which is 0.07, divided by N is 12, to the 12 times T, which is 10. So now we're going to simplify, and then what I like to do first is simplify first your exponent. And we're going to go 6,000 times, and actually you can also simultaneously simplify what's in here. So inside our parentheses, we go 1 plus, if you say 0.07 divided by 12, it's this really long decimal. We get 0.05, blah, 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 blah. And so we simplify to 12 times 10 is 120. When you get a decimal in your calculator, just leave it there. Don't round it, don't truncate it until the very end. Just leave it in your calculator. So I'm going to go 1 plus that number that we just got in your calculator. So you're going to get 1.0058, blah, 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 blah. Leave it in your calculator. Now, when you do this, you're not going to go 6,000 times the number in your calculator. You're going to do this next. So take the number in your calculator, which is 1.0058, dot, 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 goes on forever, right? Raise it to the 120 power. So you're going to take that 1.0058, leave it in your calculator the way that it is, and then do your caret key 120. Calculate that first. Then we're going to say, okay, 6,000 times that amount, which is kind of a big amount. And then, so whatever this says, it's approximately 2.00, blah, 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 blah. Multiply it now, go times 6,000, and you'll get 12,057,968, blah, 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 blah. And remember, we're trying to figure this out to the nearest dollar, or the nearest, nearest cent, because we're talking about money. So we're going to round it to the nearest cent. So this is how much we have if we compounded it monthly. But what happens if we compare it to compounding it continuously? Which one do you think would be a better investment? So let's just see. Same amount of time, same amount of money. We're going to use our compounded continuously formula, P e to the RT. So we're looking for the amount. P is still 6,000. E is the natural number, it's set. R is the rate, which is 0.07. And T is still the same amount of time, 10 years. So we're going to just plug this into our calculator at 6,000 times E. And then when you hit second natural log, or ln, it should automatically give you e to the, and then 0.07 times 10 is just 7. So if we get that in our calculator, we should come out with 657,979.8.95. So what do you think is a better investment? If we compare these two, this is definitely way better. Now, I will say there is nothing that really, you can't really invest anything that will give you a compounded continuously rate like that. But there are other financial implications to this, which is really great.